This concept is one of the most important ones to understanding Taylor series and everything that comes after power series. Understanding how we move from series, infinite sums, to functions is the conceptual gap that I think really makes this class hard. And I think if you can get that, then everything will come a lot easier to do to you. So yeah, let's do a little recap. We started off talking about sequences or infinite lists. Brackets a sub n equals a1, a2, a3, all the way up to a sub n. Just an infinite amount of numbers, right? Lots of numbers. We then converted that into series by adding all of those terms together. At that point, we took a break and we asked, well, do these series necessarily equal something that's not infinity? Because I'm sure you can imagine if a sub n, every term just gets bigger and bigger and you're adding all of them up, you're going to reach a very large number that's just going to reach infinity pretty quickly. So we spent a lot of time talking about convergence divergence theories for both sequences and series. Understanding the difference to them is important, right? We know that our sequence, we need that to go to zero. We need the sequence to converge at zero for the series to converge, but that doesn't necessarily mean converge, right? That's test for divergence. I'm sure you've talked about that. So, and I don't think it's necessary to talk about now. Regardless, yeah, we went through some of these theorems, like comparison, direct comparison, that is, limit comparison, alternating series estimation theorem, and that'll come back later, actually, for alternating series, our pure series test, our integral test, and some other ones. After we talked about convergence and divergence, we talked about, okay, well, what is the actual S equal? Can we evaluate that value? And we can in a couple ways. We learned about telescoping sums, and we also learned about geometric series, a special type of series. And now we're moving on to power series. I'm going to keep our geometric series up here because we will come back to that. And let's spend some time talking about power series because that's where the meat of this lies. What's really important about power series is that compared to all of our other series, instead of this just equaling some number, we're representing a function as a number. We can represent any number as a series, any s. Say we want s to equal 0.33 repeating, right? Equals 3/10. We can write that as a series. Actually, we need to increment that at 1. For example. So now we're doing something entirely different. Provided the series converges, for a unique input x, we're getting a unique output s. So we've taken static ones into dynamic functions. You might have seen like one of those things where, okay, we have our input x and we're going to put it into our function machine. Now I always drew it like this. F of x, and we get an output y, right? That is a really normal operation to us, and f of x will rely on PEMDAS operations or something like that. We've learned some more complicated ones, like factorials, right? But it's still essentially the same thing. All comes from that. We're doing something a little different now. Instead of passing x into this PEMDAS operations, we're passing x into some summation. Really, it's just the A because we're just adding a bunch of times. And we're still getting the same output though. So that's the key thing is these two machines qualitatively look really different, but they produce equivalent things. These guys are equal. So think about that. Really just meditate on that for a little bit. The key of what we're doing is we're just replacing the machinery of functions with the machinery of series. We spent all this time learning about series, how they work, where they converge, and now you're putting that together into a new way of thinking about series entirely, or thinking about functions entirely. So yeah, it's kind of just like relearning math. We started with definitions of things, right? We started with our sequence as infinite lists. That's kind of just giving us the bare bones. We're saying this is what a number line is, I guess. And then we're moving on to actually saying these are our numbers. Instead of saying our numbers are 1, 2, 3, we're saying our numbers are equal to these sums. Then we're learning with convergence divergence tests. We're learning where that is true, because that's not always true. Then we learned about what those numbers are exactly. And now, most importantly, we're turning those number inputs into number outputs through different machinery. So yeah, it really is just kind of like what you learned all the way back in elementary school or seventh grade or whenever you learned functions. We're just learning about a different kind of function, a different way of getting those same values. Let me draw out one way that I think might make sense to visualize this. We'll talk about e to the x a lot in Taylor series. It's a really special function. And the representation for it is pretty simple. I'm just going to assume a to the n, or a equals 0 again. I think that makes this a lot easier. We go from 0 to infinity of this summation, x to the n over n factorial. So if you're looking at that, it's that 1 over n factorial is that c to the n in our power series. We kind of know what e to the x is going to look like already. If I draw that out here, and I think where it gets really confusing is what we put here. A lot of people, we're going to sort of automatically put, if this is our output y, we're going to put n on this axis here. But that doesn't make sense because n inputs can only give us discrete points. And they're not even really going to give us the discrete points that lie along this graph. Instead of thinking it like that, think about at every point on the graph, here for example, our n is actually stretching in this direction. Or let me draw it like that. In this direction. Kind of like a z direction. So you can take this slice, you can say, this is our n, this is our a sub n, and adding them together, we'll get our n. And adding them all together, we'll get our output, our s, at that point. It is important, it is really important that this is the x. Because at this point, say for example that this is x equals 1, makes that pretty easy, then the summation we're evaluating here is summation of 1n over n factorial. That gives us an output. N always goes to infinity. That's not the bit that's changing. What's changing is the actual bound itself. Or for example, we go here, x equals 0. Our summation is different here. 0, n. over n factorial. And I hope you can see that that's just going to be 1, then all the other terms are going to zero out. So there, that is the idea behind this, is we're really trying to turn functions into these infinite sums and try to decouple your brain from understanding n as only going along x-axis to n being an entirely separate thing. N always goes to infinity. That's true no matter what you're on. And I know this is a pretty confusing drawing, and it probably makes more sense to me than it does to you. But understanding this idea is the most important thing you can do to understand Taylor series in the end. All right. Thank you, and good luck with your Calculus 2 studies.